Most of the really interesting things that we're going to learn going forward are only possible because of telescopes. Our eyes have limits. As I mentioned in the last video, we can only see a small part of the electromagnetic spectrum, and we can see it in real time. So what we'd like to be able to do is see the full electromagnetic spectrum and then record it and dissect the light. So what we're going to talk about in this video is the form and function of telescopes. Now there are three essential components to measuring the light that's coming from the stars. On the picture at right, we have a region of the sky where you can see how much variety in brightness and in color there is among the stars. Now what we want to do is take that light and learn something about the thing that's emitting the light. Like, what does this color pattern here tell us about that star? So we need to collect the light, and then we need to sort it into its component wavelengths. How much light is it giving at each wavelength in the spectrum? And then we need to have a way to detect the light and record it. So those are the three essential components to what astronomers do to learn about the stars. Now the light is collected through a telescope, and then it passes through a prism or something called a diffraction grating to separate it into components. So that takes care of number two. And then it lands on some sort of detector that records the signal. So we want to talk about that. We'll focus on the telescope part, and then at the end I'll tell you a little bit about the device that is used to detect the signal. The first telescopes, the ones like Galileo used, were based on a lens. So a lens is a rounded piece of glass, or it could be plastic, but in the early days of telescopes, they were glass lenses. They were carefully ground into the shape that would focus the light at a specific point called the focal point. And that focus point or focal point is a certain distance away from the lens called the focal length. And that focal length determines essentially how powerful the lens is. Right? If you have a really, really long focal length, that means the lens is not curved very much. And then if you have a short focal length, the lens must be curved a lot in order to bend the light really close to the lens. Now for a telescope, you typically have two lenses. I should say I skipped over this. Telescopes that use lenses are called refracting telescopes because they refract the light. They bend the light. And so a refracting telescope, a telescope that works with lenses, typically has two lenses. And the big one up front is called the objective. And then so the light from the star will pass through the objective first, be focused, and then pass through an eyepiece and then into your eye where you can see it. So there's the objective and then there's the eyepiece. Where the objective lens is called the aperture. That's the opening of the telescope, and that is the most important part of a telescope, is its aperture, its light collecting area. How much area is there to collect light? Your pupil in your eye is what allows your eye to collect light. And your pupil will grow in size, will increase in size or contract based on the light environment. If you go into a low light environment, your pupil dilates to let in more light. Your aperture increases. Now, telescopes have a fixed aperture. The bigger, the better. Now, the early telescopes were refracting telescopes, but they all had a same drawback called chromatic aberration. And it's related to what happens with light when it passes through glass. It refracts, but it also spreads the colors into slightly different angles. This is why we get the rainbow effect. Well, if you're trying to focus the light from an object and it's spreading it out into colors, that's going to create a sort of blurriness, and you might even see sort of rainbow pattern of colors, where this was white, here you get sort of the rainbow spread out. So this chromatic aberration is a problem. Here is a picture taken with a lens that has significant chromatic aberration, and here is a cleaned up image. This is a problem that you can't get around just with using a refracting telescope. You could make the most perfect lens possible. It's not a manufacturing issue. It's a physics issue with lenses. You have the light passing through a lens to be focused. The light from each color is not going to focus at exactly the same point. That's the problem. Now the picture exaggerates it a little bit, but you can see how blurry this image is. And now we're dealing with light from very, very far away. Maybe the detail we're looking, it's fine, right? If we're just looking to see, Jupiter, and you want to see it's got a great red spot on it, maybe you'll see that detail. Or maybe it'll be sort of blurred into the lines, the bands pattern in Jupiter, and you won't be able to see them. If your aperture is big enough, your chromatic aberration is less significant, but at some level of detail, it will become a problem whenever you're using a refracting telescope. So Isaac Newton invented a new type of telescope using a mirror. And because mirrors don't refract light, they reflect it, these are called reflecting telescopes. And so here's a diagram of Newton's first telescope. It's essentially the same shape. It has an aperture where light enters in, but instead of going through a lens, it actually goes through just an open aperture. There's nothing here. And it reflects off a mirror, which redirects the light off a flat mirror here, which takes it into your eye where you can see. These mirror telescopes, reflecting telescopes, do not have any chromatic aberration, and so you're able to get a much crisper image. They're also lighter, right? It's much lighter to make a mirror than it is to make a big heavy glass lens. And so this was a pretty big technological advancement in the telescope, was going from refracting to reflecting telescopes. There are lots of different designs. If you're thinking about buying yourself a telescope, we can talk about that kind of offline or online, but not through email or something. Or you can ask questions in the forum, and I can help you think about it. But there's lots of different possible designs, and it sort of depends on what you want to do, which one's the best. In particular, best for the value. For a refracting telescope, they mostly work this way, where you have the light coming in, goes through the objective lens, goes through the eyepiece. But for the reflecting telescopes, which most I would say serious amateur astronomers and certainly professional astronomers use reflecting telescopes. There's plenty of different designs. The two primary types of design are the Newtonian focus. So this is how Isaac Newton designed his, where the light comes in, reflects up to a mirror, which angles it in this way. And then there's another one called a Cassegrain focus, where the light comes in, reflects off a mirror, but the mirror directs it back down here, and the hole is down here. So you actually look from down here. Okay. But these are just different ways to accomplish the same thing, and there are some trade-offs. Now, one thing with the mirror telescopes is you're bouncing the light off and reflecting it up here, so you're having to put a mirror sort of in the way. And so you might think you have like a hole in your view, and that's true whether it's the Newtonian or the Cassegrain focus. Right? You have to bounce this off another mirror. in order to redirect it to an eyepiece or a detector. But it turns out that because you can make these mirror telescopes much bigger, the fact that you lose a little chunk of the light isn't that important, right? It's a small sacrifice to make with the Newtonian focus or the Cassegrain focus in order to not have to deal with the chromatic aberration that you would get with a refracting telescope. All right. Now, so I mentioned there's three things. There's the telescope, and so we're dividing them into two basic categories: refracting or reflecting, and reflecting are essentially the better option. Then the second thing on the list was wavelength sorting. So you'd pass it through a prism or a diffraction grating to spread it out into wavelengths, and then ultimately that light has to land somewhere to be recorded. And we're not doing all the necessary work that would need to be done to understand the universe just by looking at the light. We have to record it and compile it, and then use sophisticated analysis to learn about what's there. And the basic tool that astronomers use for this is called a charge-coupled device, or a CCD. And so you can think of this as something that goes in place of the eyepiece. So instead of your eye going there to see what's coming through the telescope, the CCD is going there to record what's coming through the telescope. And a CCD is essentially a screen where every time it's hit by a photon, it sends a little electrical signal. And the photon, as we've talked about, carries energy, and so it gets a little bigger signal if it's carrying more energy, and a little lower signal if it's carrying less energy. And so now that electrical signal is telling you what size photon, what color photon, what wavelength photon just hit, and where it hit on the CCD. And it can be converted into a digital format and recorded. So now you have information in real time, like this photon hit this point in the detector at this moment in time. And that advancement is not just in astronomy research. These CCDs are found in the digital cameras of all sorts, like the ones that you probably have in your cell phone right now. And so it's been an incredibly useful technology. All right, so that's the basics of telescopes' form and function. In the next video, we'll take a quick tour of the most powerful telescopes that are used in each band of the electromagnetic spectrum.